All right, welcome again to Good Choices. Mic check. So it's the first good choice. Audio's looking good. So next good choice. Last video. This is part of my LPIC series because last video we finished up lesson 2, part 5. We can see that's actually a really long and involved lesson. But now we've just got this very short lesson here for 103.6. And once that is complete, we've only got 2 more lessons before we can move on to the final topic and maybe even thinking about like scheduling the exam at that time. So exciting times for this series because I'm getting near the end, and I've got all my progress up here, public, free to check out, to look at on YouTube, and we'll see whether or not I pass the exam. If I do, then hooray, and you can see my trail. You can use that kind of as a way to plan if you want to use if you want to get the exam yourself, and I end up passing. We can look at my oldest video. It's about 2 months ago, so you should plan about 3 months, but it should be pretty good news, because if you were thinking, oh, I'll never get my LPIC, it'll take me a year, well, if I pass this, it shouldn't take much more than 6 months. And for about the first half of this series, you can see I was doing 11-minute videos. It was hard for me to get to that hour mark, and then I published that video where I talked about some of the things supplements I was doing, and you can see my output before and after that was through the roof. So it's like, if I pass this exam, I hope this series is gonna be one of my best series. I hope people will really use this as a way to plan their own certification studying. If nothing else, just for the timeline. But also as some direction as to like what to actually go for. Now it depends on what you want in your career. Do you want to work on site? Do you want to work a hybrid? Do you want to work remote? Do you want to focus on and then what do you believe in? Like what's your philosophies? Like, do you want to work for big companies? Do you want to work for startups? Do you want to work for mid-sized companies? Do you want to learn technologies that are owned by companies, and you'll get the support of these companies, which might be a good thing, or do you want the support more of like from a community through open source? So it just depends on what your philosophy is, what the things you believe in. But so independent of that, hopefully this series can be helpful, because you can just see, as I mentioned, the timeline. You can see kind of what I use, because the process of like choosing which exam, which study materials you use, is going to depend on your philosophy. So you can kind of see the decisions I made based on my philosophy, which is, I'm more about open source. My number one goal in my career in my life is to keep working remote. So you can see the decisions I made, and then if you have different goals or philosophies, you can kind of use that same decision-making process and branch off into whatever areas you would like to go in. So I hope this is going to be a really useful series, and I hope to get it finished up as soon as I can. So with that being said, let's move on and try to close out this lesson today. So this is 103.6, lesson 1. We're still covering the topic of GNU and Unix commands. That's the whole 103 lesson. Hopefully we'll get to 104 next. So the objective of this lesson is to modify process execution priorities. Do another mic check, and let's go. So introduction. Operating systems able to run more than one process at a time are called multitasking or multi-processing systems. Whilst true, simultaneity only happens when more than one processing unit is available. Even single processor systems can mimic simultaneity by switching between processes very quickly. This technique is also employed in systems with many equivalent CPUs or symmetric processor SMP systems. Given that the number of potential concurrent processes greatly exceeds the number of available processor units. Okay, so my systems are all using this because they all have multiple equivalent CPUs as far as I know. In fact, only one process at a time can control the CPU. Otherwise, most process activities are system calls. That is, the running process transfers CPU control to an operating system's process so it performs the requested operation. System calls are in charge of all inter-device communication, like memory allocations, reading and writing on file systems, printing text on the screen, user interaction, network transfers, etc. Transferring CPU control during a system call allows the operating system to decide whether to return CPU control to the previous process or to hand it to another process. As modern CPUs can execute instructions much faster than most external hardware can communicate with each other, a new controlling process can do a lot of CPU work while previously requested hardware responses are still unavailable. To ensure maximum CPU harnessing, multiprocessing operating systems keep a dynamic queue of active processes waiting for a CPU time slot. Although they allow to significantly improve CPU time utilization, relying solely on system calls to switch between processes is not enough to achieve satisfactory multitasking performance. A process that makes no system calls could control the CPU indefinitely. This is why modern operating systems are also preemptive. That is, a running process can be put back in the queue so a more important process can control the CPU, even if the running process has not made a system call. Okay, so next section is the Linux scheduler. Linux, as a preemptive multiprocessing operating system, implements a scheduler that organizes the process queue. More precisely, the scheduler also decides which queued thread will be executed. A process can branch out many independent threads, but process and thread are interchangeable terms in this context. Every process has two predicates that intervene on its scheduling: the scheduling policy and the scheduling priority. There are two main types of scheduling policies: real-time policies and normal policies. Processes under a real-time policy are scheduled by their priority values directly. If a more important process becomes ready to run, a less important process is preempted and the higher priority process takes control of the CPU. A lower priority process will gain CPU control only if higher priority processes are idle or waiting for hardware response. Any real-time process has higher priority than a normal process. And let's go back and review. So what is a normal process? So a normal process is a type of scheduling policy. A normal process let's ask the AI. Oh, and I have to configure my AI to not have a special prompt. So let's review the because any real time process has. Oh wait. Oh, I'm getting confused. So there are two main types of scheduling policies: real time policies and normal policies. So any real time process has higher priority than a normal process. So, okay, so I did have that right. So we've got real time processes, which are the high priority because they're happening in real time. And then we have normal processes. So both real time processes and normal processes are types of scheduling policies. They're the main ones, the ones that are used the most. Real time policies are scheduled by their priority values directly. If a more important real time process becomes ready to run, a less important running process is preemptive, and the higher process takes control of the CPU. A lower priority process will gain CPU control only if the higher priority processes are idle or waiting for hardware responses. And I don't see anything written about the normal process, but or sorry, about yeah. So that looks like something written about processes under a real time policy. I don't see anything written about a process under a normal policy. So let's ask the AI about that. Oh, you know what? And it'll just do it automatically. So yeah, let's just read what the AI says here. This looks like it's going to be pretty good. Maybe even
The
have
content you provided
good.
discusses two
Yeah.
main types of scheduling policies in the context of computer operating systems: real-time policies and normal policies.
Yes.
Here's an analysis and opinion on this topic.
Perfect.
1. Real-time policies. Real-time scheduling policies prioritize processes based on their priority values. Processes with higher priority values are given preference in accessing the CPU. This means that if a more critical or important process becomes available to run, it can preempt a less important process that is currently executing. This preemption ensures that the higher priority task gets immediate access to the CPU, which is crucial for applications where timing and responsiveness are critical, such as in embedded systems, industrial control, or multimedia applications. 2. Normal policies. Normal scheduling policies, also known as non-real-time policies, typically follow a more traditional approach where processes are scheduled based on algorithms like round-robin or priority scheduling. In these policies, preemption is not as aggressive as in real-time policies. Lower priority processes may still get a chance to execute even if higher priority processes are ready to run, which can be suitable for general-purpose computing environments. 3. Priority hierarchy. The content also highlights that any real-time process always has a higher priority than a normal process. This hierarchy is essential to ensure that critical real-time tasks are not delayed by lower priority, non-real-time tasks. This priority distinction helps maintain the responsiveness and timeliness of real-time applications. In my opinion, the differentiation between real-time and normal scheduling policies is crucial for ensuring that various types of applications can coexist on a computer system. Real-time policies provide determinism and predictability, making them suitable for applications with strict timing requirements. On the other hand, normal policies provide fairness and resource sharing capabilities, which are essential for general-purpose computing environments. The priority hierarchy between real-time and normal processes is a sensible design choice. It ensures that critical tasks are not compromised by less critical ones, thereby upholding the reliability and performance of systems that support both types of applications. In practice, choosing the appropriate scheduling policy depends on the specific requirements of the applications running on a system. Real-time policies are essential for tasks like autonomous vehicles, medical devices, and industrial control systems, while normal policies are suitable for everyday computing tasks like web browsing and word processing. A well-designed operating system should offer flexibility in scheduling policies to accommodate a wide range of application needs.
All right, that was way better than I thought it would be. That was actually pretty amazing. So, uh, as a general purpose operating system, Linux runs just a few real-time processes, and that makes sense because real-time processes are the highest priority processes, and they're always preempting each other. So if you just have, a lot of processes constantly preempting, it might not be that great of a human user experience because it's just always gonna preempt whatever you're doing. Is what I think. Might want to check that with the AI, but I think that's fair to say. So like self-driving cars, like I doubt the operating systems are like, something like for a user. I'm sure like an operating system that you would install into a self-driving car just has a really basic user interface, and it's got a lot of real-time processes. As opposed to Linux, which is kind of like the opposite, where it only has a few real-time processes, but the rest are normal processes, because otherwise it would just keep preempting what you're trying to do for something else. So most processes, including system and user programs, run under normal scheduling policies. Normal processes usually have the same priority value, but normal processes can define execution priority rules using another process predicate, the nice value, and we remember learning about this before. To avoid confusion with the dynamic processes derived from nice values, scheduling priorities are usually called static scheduling priorities, and that's actually pretty good. So now we've got static priorities and we've got scheduling priorities. I just want to hear what the AI has to say about this.
Waiting for response.
Something happened. Let me get back to where I was. All right, I was right here.
The provided content discusses the scheduling policies and priorities in the Linux operating system, particularly in the context of real-time and normal processes. Here's an analysis and opinion. In Linux, the operating system manages various processes, and how it schedules these processes for execution is crucial for system performance and responsiveness. The content highlights two key concepts. 1. Real-time processes ** Linux, being a general-purpose operating system, doesn't typically run a large number of real-time processes. Real-time processes are those that require immediate or predictable responses, often used in time-critical applications like robotics or industrial control systems. Managing real-time processes is essential to ensure they receive the necessary resources and execute promptly. 2. Normal scheduling policies * Most processes in Linux, including both system-level and user-level programs, run under normal scheduling policies. These normal processes have similar priority values. However, the content introduces the concept of the nice value, which can be used to define execution priority rules. The nice value is a way to adjust the priority of a process. A lower nice value implies a higher priority.
All right, so let me ask this: is the nice value applicable to both real-time and normal processes?
The provided content discusses the scheduling policies and priorities in the Linux operating system, particularly in the context of. No, The nice value is primarily applicable to normal
Okay,
processes in
perfect.
the
Got it.
context of Linux's scheduling policies. It is not
Got
typically
it.
used with real-time processes.
This is
The
so
nice
good.
value is a mechanism in Linux, and many Unix-like operating systems, that allows users to adjust the scheduling priority of normal
Mic
processes.
check, mic check.
A lower nice value indicates a higher priority
Mic
for the
check, 1 2.
process, while a higher nice value
Mic check,
indicates a
mic
lower
check.
priority. This feature is mainly used to influence the scheduling of
Mic
regular
check.
user-level processes to make them more or less favorable in terms of resource allocation. It allows users to control the relative importance of different processes running on the system. In contrast, real-time processes in Linux are usually managed differently. They are designed to have deterministic and predictable execution timing, and their priority is often handled through specific real-time scheduling policies, such as the Completely Fair Scheduler, CFS, for non-real-time processes
This is
and the
so
round-robin or FIFO policies for real-time
this is so
processes.
interesting to me.
These real-time scheduling policies are distinct from the
This is the kind of stuff where like people should do this. Like it's like I feel like so many times, you know, we have round robin or first in first out policies implemented in the real world, like for example with scheduling your classes for like school or something like that. You know, it's usually first in first out, and then they're usually processed round robin, right? um so let's go to the AI again and get some more information about this. This is so fascinating to me.
Certainly, both the Completely Fair Scheduler, CFS, and the Round Robin, RR, FIFO policies are scheduling algorithms used by the Linux kernel to determine the execution of processes. Let's dive deeper into these scheduling algorithms. Completely Fair Scheduler, CFS, purpose. Used primarily for non-real-time processes. Algorithm. The CFS doesn't allocate fixed time slices to processes like older schedulers did. Instead, it uses the concept of virtual runtime to ensure that every process gets a fair share of the CPU time. The less CPU time a process has had, the smaller its virtual runtime. Hence, the scheduler prioritizes processes with smaller virtual runtimes. Red-black tree. The CFS uses a red-black tree data structure to keep track of the sleeper and running processes based on their virtual runtime. This allows the scheduler to quickly select the next task to run. Sleep and wake up. The time a task spends waiting for the CPU, while it's not executing, reduces its virtual runtime. This ensures that when a task wakes up from sleep, it has a good chance of being scheduled. Granularity. There's a concept of granularity in CFS that ensures that the system still remains responsive. It prevents a currently running task from monopolizing the CPU for too long. Real-time scheduling. Round robin, RR, and FIFO purpose. Used for real-time processes that require deterministic and bounded latency. FIFO, first in, first out. When a task starts its execution, it runs until it either finishes, is preempted by a higher priority real-time task, or it voluntarily yields the processor. No time slicing in the traditional sense. If a FIFO task starts running, it keeps the CPU until it decides to release it, gets preempted, or completes. Round robin, RR. It's like FIFO, but with a time slice quantum. Once its time slice expires, the task is moved to the end of the queue of its priority, and the next task starts its execution. This ensures that tasks of the same priority get CPU time in round robin manner. Priority. Both RR and FIFO are priority based. If a higher priority task becomes runnable, it will preempt a lower priority task. Choosing between them. Real-time tasks using RR or FIFO policies should be employed when predictable and timely responses are required. CFS is more suitable for general-purpose tasks where fairness and throughput are the main concerns, rather than strict timing guarantees. Understanding these scheduling policies is vital when configuring or developing for a Linux system, especially if there are real-time requirements. It's also worth noting that while the Linux kernel provides these mechanisms, getting true real-time performance also depends on other factors like kernel configuration, hardware considerations, and the specific use case.
All right, so let me ask it. Explain to me these scheduling algorithms in the simplest way possible without losing meaning. Use simple analogies that apply to everyday life so I can understand it in an intuitive way. Explain to me each of these scheduling algorithms and the details behind them in the simplest way possible without losing any of the meaning. Use analogies for concrete everyday situations that I can use to understand these concepts intuitively.
Absolutely. Exclamation mark. Let's use some day-to-day analogies to explain these scheduling algorithms. Completely Fair Scheduler, CFS, analogy. Imagine a library with many people waiting to read a limited number of books. The librarian ensures that everyone gets a chance to read, but if someone hasn't read for a while, they're moved up in the queue. If a person has just finished reading a book, they might wait a bit longer for their next turn. Each person is a process. The book is the CPU. The librarian is the CFS, ensuring everyone gets a fair chance to read. How long each person has read or waited is their virtual runtime. FIFO,
Okay.
first in, first out, analogy. Picture a single queue at a cinema ticket counter. The first person in line gets served, then the next, and so on.
Yeah.
If a new person comes, they wait at the end of the line.
Yep.
Each person is served completely before moving to the next. Each person in line is a process.
Yes.
The cinema ticket counter is the CPU. The way each person gets their ticket before the next person is the FIFO principle. Round robin, RR, analogy. Now, consider a bakery with a single counter but a twist. Each customer can only order one item at a time. After ordering one item, they must go to the back of the line if they want more. This ensures that everyone gets a turn quickly, even if some people have larger orders.
That's brilliant.
Each customer is a process. The bakery counter is the CPU. The rule of ordering one item at a time represents the time slice in RR. After their slice, or turn, they have to wait for their next turn. In summary, CFS is like a librarian ensuring everyone gets a fair chance to read a book. FIFO is like a cinema where each person is served in the order they arrive, one at a time. RR is like a bakery where each person can order one item per turn to ensure everyone gets served quickly. These analogies help provide an intuitive grasp of how each scheduling algorithm
That's not bad. So like I feel like round robin is like it's weird to me why somebody would use round robin, because like if you imagine it like a bakery, like let's say that like it makes a lot of sense if you have like a lot of customers coming in and just ordering like a donut, a bagel. Let's say they get like a bagel and a coffee, and then you have one customer coming in and ordering, you know, like 100 donuts. So it's like that makes sense, because now that one customer ordering 100 donuts, it makes sense based on the number of customers you have. Because let's say you have 99 customers, each of them are just ordering one donut. So now each of them comes through, and now you get that one customer that orders 100 donuts. So they come to the line, you give them one donut, and then you say, sorry, you have to come through the line 99 more times to get the rest of the donuts. So what happens is those other 99 customers all get their service and they're all happy with their donuts. That one customer is not too happy, but if no more customers come in, now you serve that one customer all 99 of their donuts. So like that makes sense, and that's kind of where I don't get, like, I feel like that's not done as much in like fast food and stuff, like, because I feel like that particularly, no, I feel like it is done, because I don't know, I feel like mostly it's first in first out, like you know, you can picture really easily a cinema ticket counter, and for each person in the line you get one cinema ticket, but it's harder to imagine like it being round robin where, for let's say that you have, you know, a family play area, and there's a wife and there's 3 kids, and they're all just hanging out in the family play area. Then there's 5 people in line. The first person in line is the husband of this family, and then the next 4 people in the line are just some teenagers buying an individual ticket. So if it were first in first out, then the husband would buy 5 tickets, one for each for themselves and one each member of the family, and then the teenagers would each buy theirs. So that makes sense in that case, because to procure a ticket really doesn't take a lot of time. But let's say that to procure each ticket takes 1 minute. So now if you have the husband buying 5 tickets, it's going to take 5 minutes to get the ticket. Whereas if you had the teenagers get their tickets, it would just take 1 minute. So what you could do is, instead of having the line take 5 minutes for the husband, then 6 minutes for teenager 1, 7 minutes for teenager 2, and so on, you could have the process take 2 minutes for teenager 1 by giving the husband 1 ticket and then sending them back to the back of the line. Then you could have it take 3 minutes, 4 minutes, 5 minutes, And now the total time waited for the husband is 9 minutes instead of 5 minutes. So that's kind of interesting, and you can see, the husband gets screwed if a lot of more people come in, because we've got this line of 5 people. The husband buys 1 ticket. The husband goes to the back of the line. Now they have 4 more tickets to go, so they get 1 more ticket. Then let's say 20 people come in line. Now the husband needs to buy 3 more tickets, but now the husband needs to wait 20 more minutes just to get one of those tickets. And let's say 100 people come in. The round robin strategy is basically a strategy to favor the people that are buying fewer tickets, and it really freaking screws over people who need to buy a lot of tickets, if you think of it that way. First in, first out can screw over the people just buying 1 ticket. So let me tell the AI about this. Okay, great. So thinking about this further, the first in, first out strategy is a strategy that could really screw over the people that just want to buy 1 ticket in the theater, because then they would have to wait for the person buying a lot of tickets to get their tickets served. So let's say that it takes 5 minutes to procure each ticket. If there were a line of 5 people and the first person in line wanted to get 5 tickets, then the second person in line just buying 1 ticket would have to wait 6 minutes, the third person 7 minutes, and so on. But instead, you could use the round robin strategy to favor these people just buying 1 ticket, because then you would send the person buying 5 tickets to the back of the line after they bought their first ticket, and then the second person in the line would only have to wait 2 minutes, third 3 minutes, and so on. But the problem with this strategy is that the person buying 5 tickets could potentially get screwed over and have to wait hours and hours if more people come in the line. For example, if the person buying 5 tickets bought their 1 ticket and then only had to wait for the 4 people to get through, then that's not that big of a deal if they're only buying 1 ticket, because they would only have to wait 9 minutes. But say that the person buying 5 tickets made it to the front of the line to buy their second ticket and 20 more people got in the line, then they'd have to wait 20 minutes. And then after their third ticket, if 100 people got in line, then they'd be completely screwed over and they wouldn't get their tickets in time to see the movie. Is this understanding correct? Is there anything you would add to this? What a
Your
world
understanding
we
is
live in.
spot on and very well thought out. Let's summarize and potentially add more insight. FIFO. Pros. Straightforward. Each person is served completely based on their position in line. Good for scenarios where interruptions can be costly or problematic. Cons. As you pointed out, if someone has a large order or a task takes a long time to complete, it can cause others to wait for an excessively long time.
Yes.
This can lead to what's known as head of line blocking. Round robin. Pros. Provides fairness on a per turn basis. Everyone gets a chance in a timely manner, which can increase system responsiveness and is especially favorable for those with small orders. Cons. Tasks with large orders might get considerably delayed if there's a consistent influx of new tasks. In worst-case scenarios, if there's a constant stream of new tasks arriving faster than the original long task can complete its turns, it might seem like the long task is being starved of resources, even if it's technically still getting turns.
Exactly.
Your cinema example highlights the trade-offs between these two strategies very well. FIFO can be likened to the traditional way of buying tickets where one person completes their entire transaction before the next person starts.
Right.
Round robin is more akin to a fast lane system where everyone gets to make a small portion of their order before moving to the back of the line. Additional points. Real-life scheduling often uses a mix of strategies to handle different scenarios. To prevent the extreme case in round robin where a long task might seem to be getting starved, many systems implement priority aging. This means if a task has been waiting too long, its priority gets artificially boosted, so it gets served more quickly.
Interesting.
This mechanism ensures that no task waits indefinitely. Another aspect to consider is predictability. In real-time systems where tasks need deterministic guarantees, neither of these methods might be suitable on their own without modifications or additional rules. Your observation clearly demonstrates the strengths and weaknesses of both methods, and indeed, in systems design, it's often a balancing act to ensure fairness, efficiency, and timeliness.
So that's interesting. So now I know about weighted round robin. I think this is weighted round robin. So basically what you do is you have that person in the front of the line that they need to buy 5 tickets. And then you have the 4 people behind them that each need to buy 1 ticket. So round robin would be okay, you get one ticket, go to the back of the line, and then go through the line 4 times to get the rest of your 4 tickets. In the meantime, these 4 people all get their ticket, and they only have to wait a very small amount of time, whereas before they would have to have waited a lot longer. So what you can do is to prevent this person from getting screwed over. So you can assign them a number for each time they make it through the line. So let's say they buy 1 ticket. So you basically you can look at the amount of tickets they have already, and then you can move them in line based on that. So they buy 1 ticket. Okay, it takes 1 minute to get the ticket. The second person in line, 2, third, 3, 4th, 4, 5, 5. Okay, great. So the person at the back of the line only takes 5 minutes to get served. But now the person at the front of the line, since he needed more tickets, got screwed over, has to wait 9 minutes to get their next ticket. So what you do is you say, okay, well, you only have 1 ticket. You need another ticket. You're in front of the line now just because you waited for this long. Okay, well, go to the back of the line to get your 3rd ticket, but now that you could say go to the middle of the line now because you already have 1 ticket. Or you could say, okay, well, you have 3 tickets already. We know you waited for a long time. Come to the front of the line. We don't want you to wait anymore. So that I think that's what weighted round robin is instead of sending someone to the back of the line every time, you take into account how many times has this person gotten to the front and not got everything they needed. If that starts to add up, then let's just prioritize this person now because we know that they've been waiting for a long time. So I never really understood that. So, oh my God, what a world we live in. It's amazing. Okay, great. Now please Okay, great. Now, please fill in my understanding of the completely fair algorithm so that I understand it as completely as I do first in, first out, and round robin.
Absolutely. Exclamation mark. Let's stick with the cinematic analogy to discuss the completely fair scheduler, CFS. Completely fair scheduler, CFS. Analogy. Imagine a cinema where there's a point system instead of a traditional line. Every time a person gets a ticket, they accumulate points. The goal of a ticket vendor is to ensure everyone's points stay as close as possible. So, someone with the least points gets to buy a ticket next. When you first arrive, you have 0 points, so you're prioritized to buy a ticket. After you bought your first ticket, you gain points. Someone else, who hasn't bought a ticket yet, will now have fewer points than you. Thus, they get to buy next. The more tickets you buy, the more points you accumulate, which means you'll likely have to wait a bit longer for your next turn if there are others with fewer points. Let's say you bought 3 tickets, accumulated many points, and decide to take a coffee break. In the meantime, others are buying tickets and accumulating their own points. When you return from your break, your relative point count may now be lower than others because they've been active while you were not. So, you're back in the game without having to wait too long. Pros. CFS works to ensure everyone gets a fair share of the ticket buying time based on points. It's a balance between FIFO and round robin. It won't let someone hog the ticket counter like in pure FIFO, but it also won't make a big ticket buyer go to the end like in round robin. It provides a smoother experience. No one feels drastically penalized for either buying too many tickets or too few. Cons. For tasks that need predictable source times, like real-time tasks, CFS might not always be the best choice. That's because its main goal is fairness over time, rather than strict timing guarantees. To wrap up, if FIFO is a straight line where one completes their entire order and round robin is like a fast lane where everyone makes a small order before moving back, the completely fair scheduler is like a points-based system ensuring everyone gets a turn at the ticket counter based on their history of purchases and waiting times. The ultimate aim is to balance everyone's points over time.
Alright, I gotta take a quick break. I'll be right back. Alright, so this is kind of fascinating because it sounds like my understanding of weighted round robin, which, you know, I'm getting ahead. It's not, they just kind of pointed that out, but, you know, I'm kind of getting ahead of myself, is that it is the same as completely fair scheduling. So let me ask it. What is the difference between completely fair scheduler algorithm and weighted round robin?
Great question. Let's dive into it using simple concepts. Completely fair scheduler, CFS. Concept. CFS operates on the idea of ensuring that each task gets a fair share of the CPU based on its virtual runtime. This runtime represents how much CPU time a task has received. Tasks with less CPU time, thus smaller virtual runtime, get scheduled next. Analogy. Think of a playground seesaw. CFS aims to keep the seesaw balanced. If one side, representing a task, has been up in the air for too long, hasn't had much CPU time, the seesaw will tilt to let that side down, giving it a turn on the round, CPU time. Weighted round robin, WRR. Concept. In traditional round robin, RR, every task gets an equal time slice of the CPU before moving to the next. However, in weighted round robin, tasks have assigned weights, and these weights determine the length of their time slices. A task with a higher weight gets a longer time slice than one with a lower weight. Analogy. Imagine a buffet where everyone can eat in turns. In traditional RR, everyone gets, say, 2 minutes each to pick their food before the next person's turn. In WRR, however, some people, tasks, have VIP passes higher weights. The VIP might get 4 minutes, while a regular person gets only 2 minutes.
Okay, that makes
Key
sense.
differences. Basis of operation. CFS. Works on the principle of virtual runtime, which is dynamically adjusted based on the CPU time a task gets. It's all about fairness over time. WRR. Works on pre-assigned weights that dictate how long each task time slice is. It's about distributing CPU time based on these stack weights. Priority handling. CFS. While CFS does not natively operate on task priorities, Linux implements nice values that can influence a task's virtual runtime, offering a way to give tasks different shares of the CPU. WRR. Priority is explicitly handled using weights. Tasks with higher weights are deemed more important and get longer CPU time slices. Predictability. CFS. It might be harder to predict exact timings for when tasks get CPU time due to the dynamic nature of virtual runtimes. WRR. Given you know the weights and the order of tasks, it can be more predictable since each task's CPU time slice is directly proportional to its weight. In essence, while both aim to provide fairness in task scheduling, CFS does so by dynamically tracking how much CPU time tasks have gotten, while WRR uses pre-assigned weights to allocate CPU time slices.
I really liked that buffet analogy. Please use that analogy to talk about CFS.
Of course, let's extend the buffet analogy to explain the completely fair scheduler, CFS. Completely fair scheduler, CFS, and the buffet. Imagine a buffet where people are lined up to fill their plates, but there's an all-knowing host who ensures that everyone gets a fair share of time at the buffet table, based on how much time they've already spent there. 1. Tracking time. Everyone wears a stopwatch around their neck. This stopwatch isn't tracking real time, but instead tracks the amount of time each person has spent at the buffet table.
Interesting.
2. Buffet time allocation. When you first arrive, your stopwatch reads 0, meaning you haven't had any time at the buffet. The host sees this and quickly ushers you to the buffet.
Oh, okay.
As you spend time filling your plate, your stopwatch counts up. 3. Balancing access. After a little while, someone else with less buffet time might arrive or be spotted by the host. To ensure fairness, the host might politely ask you to step back and allow this new person to access the buffet, balancing out the buffet time between attendees.
Interesting.
4. Returning guests. If you decide to take a break and sit down to eat, your stopwatch pauses. During your break, others are accumulating buffet time.
Wow.
When you decide to return for seconds, the host will consider the time on your stopwatch in comparison to others.
Interesting.
If there are others who've been at the buffet significantly more than you, you'd be given priority.
Interesting.
Fairness over time. The key here is that over the duration of the meal, the host ensures that everyone's stopwatch reads roughly the same amount, meaning everyone has had roughly equal opportunity at the buffet table.
Interesting.
In this analogy, the buffet table represents the CPU. The people at the buffet are the tasks processes wanting CPU time. The stopwatch each person wears is the virtual runtime. It tracks how much CPU time each task has had. The all-knowing host is the CFS algorithm, ensuring everyone gets a fair turn at the buffet based on their stopwatch time. So, in the world of CFS, it's like having a buffet where the objective isn't just to ensure everyone gets food, but to ensure everyone gets an approximately equal time at the buffet table, regardless of how many times they visit or how long they spend eating in between.
That's fascinating. Okay, I think I understand it. So let's think of it as a buffet. You know what? I kind of, this is kind of lazy, but okay, great. Now let's think of it as a buffet and go through and review each of the algorithms we talked about, including weighted round robin.
Alright, let's set the stage. We are at a grand buffet, and we have different strategies, scheduling algorithms, for how guests access the buffet table to fill their plates. 1. First in, first out, FIFO. Buffet analogy.
Yeah.
As guests arrive, they form a simple queue. The first person in line goes to the buffet table and fills their plate completely before the next person starts. If a guest wants to fill multiple plates, they do so consecutively, and everyone else waits for their turn.
Right.
Implication. A guest who takes a long time or fills many plates causes everyone behind them to wait, even if those weighing only want a small serving.
Yes, exactly.
2. Round robin, RR. Buffet analogy. Every guest gets a
Wow.
fixed amount of time, e.g., 2 minutes at the buffet table. When their time is up, they move to the end of the line, regardless of whether they've filled their plate completely or not.
Yes.
Implication. This strategy keeps the line moving and ensures that everyone gets a chance at the buffet in a short period. However, those with bigger appetites might need to cycle through the line multiple times.
Yes.
3. Weighted round robin, WRR, buffet analogy. This time, guests have badges indicating their weight or priority. Some badges allow 1 minute at the buffet, some allow 2 minutes, and VIP badges might allow 4 minutes. So, a VIP guest gets more uninterrupted time at the buffet compared to someone with a lower weight badge.
Yes.
Implication. Certain guests are given more importance, and thus, more buffet time in one go. It provides a balance between fairness and priority.
That's so
4.
good.
Completely fair scheduler, CFS. Buffet analogy. Here, every guest has a stopwatch that tracks how much time they spend at the buffet.
That's so good.
The host ensures that over time, all guests have roughly the same reading on their stopwatches. If your stopwatch shows less buffet time than others, you get priority. After you've spent some time, someone else might get the chance, especially if their stopwatch indicates they've had less buffet time. Implication. It's all about balancing everyone's buffet experience. No one gets left out, and no one monopolizes the table. Over the dinner's duration, everyone should have had roughly equal chance to access the buffet, regardless of how many plates they've filled or how many breaks they've taken. So, using the buffet setting, these scheduling algorithms dictate how guests, or tasks in the computer world, access the buffet table, or CPU, to ensure a balance between fairness, efficiency, and priority. The chosen algorithm can significantly impact the guest's experience, just as it can for tasks in a computer system.
That's absolutely fascinating. What a world we live in. That is, I never see. The thing is, like, I learned about this in school. I've worked on QoS, and I never understood it this intuitively as I do now. Like, wow, what a world we live in. Now, tell me, are there any more algorithms that are relevant to this that we didn't cover? What is the best and most commonly used algorithm of the ones that we covered or not?
Yes. There are several other scheduling algorithms beyond the ones we've covered. However, the best choice of scheduling algorithm often depends on the specific use case and system requirements. Here are a few more algorithms. 1. Shortest job next, SJN, shortest job first, SJF. Concept. The task with the shortest expected execution time is scheduled next. It's non-preemptive, meaning once a task begins execution, it runs to completion. 2. Shortest remaining time first, SRDF. Concept. A preemptive version of SJN. If a new task arrives with a shorter remaining time than the currently executing task, the CPU scheduler will swap out the current task. 3. Priority scheduling. Concept. Each task is assigned a priority, and the task with the highest priority, usually the lowest numerical value, is executed next. It can be both preemptive and non-preemptive. 4. Multi-level queue scheduling. Concept. Tasks are divided into different groups or queues based on properties like foreground, background tasks, memory size, etc. Each queue can have its own scheduling algorithm. For instance, foreground tasks might use RR while background tasks use FIFO. 5. Multi-level feedback queue. Concept. Similar to multi-level queue scheduling, the tasks can be moved between queues based on their behavior and estimation of CPU burst time. Which is the best or most commonly used? In general-purpose operating systems, the completely fair scheduler, CFS, is widely used in many modern general-purpose OS like Linux because it provides a good balance of fairness and throughput. However, it's essential to remember that Linux and other OS might employ a mix of scheduling strategies to cater to a variety of task types. In real-time operating systems, RTOS. RTOS is often used priority-based scheduling to meet strict timing requirements. Round-robin or FIFO might be applied to tasks of the same priority. In batch systems, SJN, SJF, or its variants are sometimes used because they can minimize waiting time and optimize throughput. Ultimately, there's no one-size-fits-all best scheduling algorithm. The best choice depends on the specific requirements of the system, such as response time, throughput, fairness, and the predictability of tasks. It's common for operating systems to employ a combination of strategies to ensure efficient and fair CPU usage.
Who came up with all of this, and what is the history of the development? How did they think of this, and how could similar thinking and discovery and development be used to develop new algorithms that are better?
The development of scheduling algorithms has a rich history that spans the evolution of computing. It's intertwined with the need to optimize resource allocation and computing systems as they grew in capability and complexity. Here's a brief overview of the history and thinking behind these developments. Historical development. Early computers, 1940s to 1950s. Early computers did not require complex scheduling. They operated in batch processing mode, running one job at a time from start to finish. Multiprogramming, late 1950s to 1960s. With advancements in technology, computers could keep multiple programs in memory. This led to the need for scheduling algorithms to decide which program to run next. The development of algorithms like first come first serve, FIFO, and shortest job next, SJN, can be traced back to this era. Time-sharing systems, 1960s-1970s. These systems aimed to share computing resources among multiple users, leading to the development of round-robin scheduling and priority scheduling. Time-sharing systems prioritized interactivity, requiring algorithms that could rapidly switch between tasks. Modern operating systems, 1980s present. As OS became more sophisticated, they needed more nuanced scheduling approaches. The completely fair scheduler, CFS, in Linux, for instance, emerged as a response to the need for both fairness and efficiency. Thinking and discovery. Problem identification. At each stage in the evolution of computing, engineers and researchers identified bottlenecks or inefficiencies in system performance. Empirical testing. Early scheduling methods might have been based on intuitive ideas, but they were refined through empirical testing, where different scheduling approaches were tried out and their performances were measured. Mathematical analysis. Especially in the realm of theoretical computer science, many scheduling algorithms have been studied through formal mathematical models, which help in predicting their behavior and finding optimal solutions for specific problems. Developing better algorithms. Understanding current limitations. A deep understanding of the present systems, their bottlenecks, and limitations is the starting point. Interdisciplinary approach. Many advancements in computer science come from borrowing ideas from other disciplines like economics, biology, or physics. For instance, game theory from economics has been used to develop algorithms for resource allocation. Continuous testing and iteration. Algorithms can be refined over time by continuous testing under varied real-world conditions. Fostering collaboration. Academic research, open source contributions, and industry collaboration can lead to new ideas and refinements in existing algorithms. Look beyond traditional computing. With the rise of quantum computing, neuromorphic computing, and other non-traditional computing models, there will be a need for entirely new scheduling paradigms. In essence, the development of scheduling algorithms and any new algorithm comes from a mix of theoretical study, empirical testing, creative problem solving, and understanding real-world requirements. By recognizing the ever-changing nature of technological challenges and remaining open to new ideas and approaches.
All right, I want to ask it more things because I'm just fascinated right now. It's got my full attention. I want to stay on topic though, and keep learning about the LPIC. What I'd like to ask it about is, if you follow me on LinkedIn or anything, one of the problems I kind of want to solve right now is the problem of information. I just want everyone to be satisfied with the information they're getting, and to be able to have information that is of a quality where they're just doing all the right things, like financially they're making good decisions, their weight is good, they're not having health problems because they just they have all the information they need. They don't believe that they don't believe in it's like, I believe that right now one of the biggest problems facing humanity is a crisis in information. And if we all had, if we all were operating under the purview of what I call good information, like a lot of problems would just resolve naturally. It would solve the obesity crisis. It would solve alignment issues with AI, because and it would resolve climate change. It's but that's my personal. This is just not related to the LPIC, unfortunately. I'm kind of tempted to just ask it one quick question. So one quick question for you, and please keep this brief because I'm off topic right now. I want to learn about the LPIC. I'm doing a series for YouTube, but the question I have is, can any of this be used to solve what I call the information crisis, where people are operating under and continually exposed to low quality and, in fact, a lot of the times harmful information that they are using to make decisions that often have very poor outcomes?
Certainly. The principles behind scheduling algorithms can be applied to the information crisis in the form of content ranking or recommendation algorithms.
Yes.
Here's a brief overview. Priority-based filtering. Just like in priority scheduling, content sources can be ranked based on their reliability and credibility.
Yes.
Authoritative sources can be given higher priority in information feeds.
Yes.
Fairness algorithms. Drawing from the completely fair scheduler, platforms can ensure that a diverse set of perspectives from credible sources give visibility, preventing echo chambers.
Mm-hmm.
Time-based rotation, round robin. To prevent overexposure to one type of content or one perspective, platforms can rotate through different credible sources or topics, ensuring users get a varied information diet.
Yes.
Feedback mechanisms. Similar to the multi-level feedback queue, users' feedback on content quality can be used to adjust its ranking or visibility.
Yes.
User education and transparency. Making users aware of how information is ranked and the source's credibility can empower them to make more informed decisions. Incorporating these scheduling and ranking principles can help platforms deliver higher quality information to users, but the challenge also lies in balancing commercial interests, user engagement, and information quality.
Mm-hmm.
Collaboration between tech companies, governments, academia, and civil society will be essential to address the information crisis comprehensively.
Yeah, this is way off topic, but just between you and me, the entire public internet all throughout space and time for all of eternity. I just think Facebook and they just came out of, Mark Zuckerberg just developed it on his own in a, it's I feel like he's selling apples, and his apple trees are of a certain quality, and the whole world, there's apple trees everywhere of all kinds of different varieties and qualities, and I feel like there's an opportunity to sell different apples that people are more interested in buying. Okay, he can have the most widespread, publicly available apples, the Red Delicious apples that nobody likes, and people think apples taste horrible because they're eating Red Delicious apples. And then somebody else can sell, what are they called? A Golden Delicious, or the apples that really popped off recently. I think they're Golden Delicious. I can't remember. And it's like, more people will buy this apples regardless of how available Red Delicious apples are. There's a point where people are just selling Red Delicious apples because they've always sold Red Delicious apples, and people are buying Golden Delicious apples. So like I feel like we're in this time in history right now where like we just see an apple as being a Red Delicious apple, and people haven't really tasted other kinds of apples. And like, this is what we're getting right now with social media. We have TikTok, we have Instagram, we have Twitter, we have Facebook. These are all apples, and I feel like the characteristics of these apples are similar. And I just think it's time for like a totally new apple. And like I feel like this sort of thing, like ranking sources based on reliability and credibility, ensuring that echo chambers are popped by using fairness algorithms, preventing overexposure of one type of content or perspective, accepting quality content feedback, and then educating users about where this information come from, because now I'm really off topic, but most mis and disinformation comes from very, very small user base. So it's like in Who Wants to Be a Millionaire, like very commonly the Ask the Audience is a really powerful one, because the people who don't know the answer are drowned out by the people who do. But what's happening right now in social media is the opposite. The people who don't know but are the loudest, the most active, the most visible are the people that get listened to, that can tell the most compelling story. So it's like, people need to be aware that I'm consuming a news story, I'm consuming health advice from this really small, subsection of the audience. And that when, there's a larger pooling of opinions and expertise, generally you can get a more accurate answer. So a lot of times right now on Facebook and stuff, people are exposed to mis and disinformation a lot because the platform doesn't tell them or doesn't schedule or prioritize their viewing based on the consensus around this information. It just floods them with what the most radical, extreme, 12 people on the internet are saying, and it just completely discounts the concatenated view of millions of people all over the world, just in favor for what these 12 people have to say. So yeah, but way off topic. Let's get back to the LPIC, and let's talk about so let's keep reading. We'll read this again and then move on to the next section. So any real-time process has higher priority than a normal process. As a general purpose operating system, Linux runs just a few real-time processes. Most processes, including system and user algorithms, run under normal scheduling policies. Normal processes usually have the same priority value, but normal policies can define execution priority rules using another process predicate, the nice value. To avoid confusion with the dynamic priorities derived from nice values, scheduling priorities are usually called static scheduling priorities. The Linux scheduler can be configured in many different ways, and even more intricate ways of establishing priorities exist, but these general concepts always apply. When inspecting and tuning process scheduling, it is important to keep in mind that only processes under normal scheduling policy will be affected and not the ones under the real-time scheduling policy. All right, so next is reading priorities. I'll take a quick break and be right back. All right, I'm back. We're at about the hour-minute mark, but let's see how far. I know this is a really short one. So let's get down to before the exercises, and then end the video there. So next section is reading priorities. Linux reserves static priorities ranging from 0 to 99 for real-time processes, and normal processes are assigned. Wait, what? Linux reserves static priorities ranging from 0 to 99 for real-time processes and normal processes. I think they're missing a that here. That are assigned to static priorities ranging from 100 to 139. Meaning that there are 39 different priority levels for normal processes. Lower values mean higher priority. The static priority of an active process can be found in the sched file, located in its respective directory inside the /proc file system. All right, so let's go to the lab and look at that. Oops, it's LAB, not LBS. Okay, and we'll do grep, and then it's gonna. This is a glob expression, so it's gonna begin with PRI with a P, and then the next characters will be RIO, and /proc1 sched. There we go. So yeah, we got the same priority, 120, which is kind of mid priority. Yeah, so mid, maybe upper end. So there's 39 different values. So yeah, it's like right away, right in the mid value. I think it's one tick over. There is no exact mid because it's a. Oh, there is an exact mid. So maybe it's the exact mid. I don't know. So as shown in the example, the line beginning with PRIO gives the priority value of the process. The PID-1 process is the init or the systemd process. The first process the kernel starts during system initialization. The standard priority for normal processes is 120 so that it can be decreased to 100 or increased to 139. The priorities of all running processes can be verified with the command ps -capital A and lowercase l or ps -lowercase e lowercase l. So they did lowercase e lowercase l. I'm going to do the other one. PS uppercase A lowercase l. There we go. And let's see if we got the same headers. Yep, FS, UID, PID. Yep, looks good. And then let's look for the priority. Yep, so it's PRI. So we can see we've got values that aren't 100 through 120. I'm kind of surprised to see that. Yeah, so hopefully they explain that. The PRI column, the PRI column indicates the static priority assigned by the kernel. Note, however, that the priority value displayed by PS differs from that obtained in the previous example. Due to historical reasons, priorities displayed by PS range from -40 to 99 by default. Oh, that's annoying. So the actual priority is obtained by adding 40 to it. Okay. Can we not? Can we please not? It is also possible to continuously monitor processes currently being managed by the Linux kernel with the program top. As with PS, top also displays the priority value, oh my god, differently to make it easier to identify, to identify real-time processes. top subtracts the priority value. And what do they mean by that? Do they mean the priority value from the column here? Do they mean the priority value that's 100 through 139? By 100, thus making all real-time priorities negative. Wow. With a negative number or RT identifying them. Therefore, normal priorities by top range from 0 to 39. Okay, well, that's not so bad because it's just dropping the 1. But this is kind of bad. It's negative 40 to 99. It's not even the same range of numbers. So I need more information about this. Let's ask the AI.
The content you provided appears to be an explanation of how process priorities are displayed in the context of the Linux kernel and two commonly used command line tools, PS and top. It's discussing how the displayed priority values may differ from the actual priority assigned by the kernel due to historical reasons and how these tools interpret and display the values. Here's an analysis and opinion. 1. Static priority and displayed values. The passage explains that the kernel assigns static priorities to processes, and these priorities can be seen in the PRI column. It points out that the PS command displays priority values differently than what is obtained from the kernel. This discrepancy arises because PS displays values ranging from -40 to 99 by default. To obtain the actual priority, you need to add 40 to the value displayed. This is important for understanding and managing process priorities accurately. 2. Real-time processes. The passage mentions that top is another command used for monitoring processes, and it also displays priority values.
Okay, so I'm just going to say use top, use top, use top, use top. So then I'm going to ask it one more question. Is there anything a newcomer can do to make sure that they are not bamboozled by all of this? So okay, you got to get good. Don't be a noob. That's the answer. So yeah, read documentation, practice, online tutorials, get the LPIC. That's the answer. All right, so note to get more details from the PS command, additional options can be used. Compare the output from this command to the one in our previous example. Okay, so this is probably going to be on the test. It's going to say like, oh, like print out only specific columns. I'm expecting that to be on there. So let's now notice that we're piping it into this head here. So let's enter this in, see what the difference is. Okay, and then let's look at what it was before. So okay, and I'm remembering what head does now, but let's get help on it regardless. Okay, so head prints the first 10 lines of a file or of input. So we know what the pipe does. It converts output of a command to input and then passes it to the next command. So it doesn't do it from a file, and we can see it does it. If you don't feed it a file, then it goes from the with no standard. It goes from the standard input, which we get through this pipe character. So there we go. There's the first 10 lines right there. Now let's get the last 10 lines. How do we do that? 3, 2, 1. We use tail. All right, so next section is process niceness. Every normal process begins with a default nice value of 0, which is priority 120, and we know now because we're not noobs. The nice name comes from the idea that nicer processes allow other processes to run before them in a particular execution queue. Nice numbers range from -20, less nice, high priority, to 19, more nice, low priority. And this is for normal processes. Linux also allows the ability to assign different nice values to threads within the same process. The NI column in PS output indicates the nice number. Only the root user can decrease the niceness of a process below 0. It's possible to start a process with a non-standard priority with the command nice. By default, nice changes the niceness to 10, but it can be specified with the option -n. So -n, we're going to give it a 15. So that's very nice. Like that, kindness is key. And this process here of tarring this backup file is now not going to take a very high precedence. In this example, the command tar is executed with a niceness of 15. The command renice can be used to change the priority of a running process. The option -p indicates the PID number of the target process. For example, okay. So that's the process number. I kind of want to do some of my own exercises with this. Let's get through the reading, and then I might do a little bit of experimentation, but I'm gonna try to end this. So the options -G and -U are used to modify all the processes of a specific group or user, respectively, with renice plus 5 -G users. The niceness of processes owned by users of the group users will be raised by 5 in 5. Besides renice, which is used for running processes, the priority of processes can be modified with other programs like the program top. On the top main screen, the niceness of a process can be modified by pressing R and then the PID number of the process. So there we go, it shows up there, and then we can change it. The message PID to renice, default PID equals 1, appears with the first listed process selected by default. To change the priority of another process, type its PID and press enter. Then the message renice PID1 to value will appear with the requested PID number, and a new nice value can be assigned. Okay, so that's it for that section of the reading. Next will be the guided exercises and the explorational exercises. But before then, I do want to close out this video. We're at the 112. That's a good length for the video. By doing a little bit of experimentation, if we use this jobs, we can see some jobs there. We don't have any. If we do sleep 60 or 50, that's fine. And then we want it to run in the background, so we'll do a ampersand. And now we do jobs. Now we've got a running one. If we do sleep 60, Control Z, jobs. Now we've got a running and a stopped process. So we can change the nice value on these by using nice on the stopped one, and then renice on the running one. Alright, so let's do jobs again. I think time moves pretty fast, so I'm not sure how much time is left on this. Let's try a nice -n 15. I would like to see what is the nice value of these, or like what is the priority of these already. So I think we can do PID of and then sleep. There we go. And now this one finished. 50 seconds has gone by. So we've got only the stopped job right now. But let's try to get the yeah. So here we go. So we've got we got it of 80. So here we go. So we can do top on dash P for the process ID. There we go. Now we're setting top, which shows it a lot better. Priority is 20, so that's like 120 for non-noobs. And yeah, so I guess we can try changing it, assuming it's a normal process. I'm not sure if that is the case. So we can do nice dash N on that. Let's try it. So nice dash N 15. Now what I'd like to do, actually, let's go to jobs and let's go to kill that, and then we'll go to jobs again. Oops. So let's go to jobs, help, and then we'll let's do a kill %2, and then jobs. Yeah, there we go. Now it's terminated. So what I want to try to do is create some messages. So let's say if we go echo hello world. Okay, so let's do this. Let's do sleep 5 and then like that. So now it will sleep for 5 seconds. And then once it's done sleeping, it will do hello world. So let's try to first of all, let's suspend this. And then let's look at jobs. Okay, so we've got one job. So let's bring it to the front. So we're going to do FG, foreground, on job number 1 there. And then we'll do a jobs. Oops. Okay, well, what happened? Is it going to print out hello world in 5 seconds? No, I don't see it. Okay, well, that's weird. What about, what if we do BG? 4% one? No such job. Okay, so that's interesting. It just kind of didn't really do anything. What about FG on echo? Is it no such job? So I don't have any jobs, but remember, let's do a top, or let's do a PID of sleep, PID of echo. Okay, so I guess I don't have any of those processes going, but you can see what I'm trying to do is I want to try to make these now we can see sleep 5 there, echo out hello world. Let's do it with sleep 1. There we go. So sleep 1 does it faster. So I'm going to say hello. So I'm going to say first is what we're going to do. And then I'm going to do second here. And let's just do 3. 5 seconds is kind of a long time. Okay, so you could see what I'm trying to do. Hopefully, what I'm trying to do is have this process here of sleep finish and then echo out first when it's done, and then I want to have this process of sleep here finish after 3 seconds and echo out second. So if we were just to have these at the same priority, the hypothesis here is that we would see first come out first and then second come out second. But if they were at different priorities, so that this one had a much higher priority than this one, this had the lowest priority, this had the highest priority, then we would see second print first and first print second. So that's basically what I'm trying to do with priorities. Let's do this. Let's go like this. Now the thing is, we're dealing with 4 processes here, so I'm not sure But the thing is, like, the command should run left to right, right? I have no idea. Yeah, so here we go. We've got first printing out, then we've got second printing out. So what I'd like to do is change the process of this first sleep to be the lowest, and then of this second sleep to be the highest. So what if I do this? What if I go like this, and then I suspend it, and then let's see what jobs I have. So I just have that one job, so we'll do FG %1. Brings it to the front. Okay, so that doesn't quite work the way I was expecting. But we can see this is working the way I expected. It prints out first, then it prints out second. First comes out after 1 second, second comes out after 3 seconds. But what I'd like to see is the niceness of these. So let's try changing the values. We're going to change it to 100. I just want them to hang for a while. And then 300. Oh, but the thing is they're going to hang like that. So, and then we'll make it run in the background by having another ampersand like that. There we go. And now we got a process ID. So now we can do top-p 4957. Okay, so but the thing is, like, this has one priority value. So I'm gonna delete out of this. And then I'm going to go to jobs and delete that job. Okay, so now what I'm going to do is do it in 2 parts, so that each part has its own process ID. Okay, so here's the first part. We should get a process ID for that part, and we do 4962. And then here's the second part. We should get a process ID for that part, and we do 4964. So now let's do top dash PID or dash P, and then we'll do 4962, and then we'll do dash P again. I think that's how it works, and we'll do 4964. There we go. So now we've got our 2 processes. We've got them with the same priority number. So if we were to, we can cancel those 2 processes, and then we can do the same thing with like 5 and 10 seconds, and then we'll see which one finishes first. So let's do that. We're going to go to jobs. We're going to kill the jobs. Okay, and then we're going to do a jobs again. Okay, so now they're terminated, and then we're going to run these commands again, but let's do 10 and 20 seconds. Okay, so that's going for 10. Oops, and I forgot to do it in the background. There we go, that's going for 10. And now let's have this one go for 20. Oops, for some reason. You know what, let's do this. Let's prepare it in a notepad file. Okay, so for 10 and 20, we're going to just do 10 and 15. That'll be better. Okay, and then we'll do a jobs, make sure nothing's still running. Nope. Put this in. Yep, paste anyway. So now we've got these 2 processes running. The first one is 4973. The second one is 4975. And they're of the same priority. So what I want to do now is take the standard output, which is the process ID of each command, and I want to pipe it into a command to change the niceness value. So what we could do is pipe xargs, and then we'll say PID, and then we'll pipe it to a command that will change the niceness based on the PID. So that command would be nice, I believe. Yeah. So it would be nice dash n, and then we'll give it the lowest niceness in the range of -20. So the lowest niceness, where's the least nice, that would be -20. Yep, and then let's look at the help for nice. Hopefully we can do a priority ID on it. Now we can see we got first and second printed out here. Yep, and now they're both done. So that worked as expected. First was printed first, second was printed second. Let's look at the help for nice. So can we pass it a process ID? So we have to have it run against a command. So let's run it. Let's do that. Let's run it against this sleep command here. So we're going to do nice minus -n minus 20, and we'll run it against this set of commands here. And then we're going to do nice -n and then the highest one, which is 19, and run it against this set of commands here. And let's see which one prints out first. So we'll set the first one to 5 and the second one to 15, and we'll expect it to print first and second. Oh, and it looks like you need sudo permission for nice. All right. Cancel. Oh, so it looks like it actually went through. Do we have any jobs? Don't have any jobs. Okay, so now let's try it. Okay, so it looks like both of these jobs are stopped now, which is kind of interesting. Is it because we need to renice them? Let's try it like this. So we've got let's try it like this. Okay, so now we're just applying it to this echo command. If we were to take out the nice version and just do it, it would obviously do first and second because we're doing it at different times. But let's try it like this. Interesting. Why are these stopped? Let's ask the AI. So I am doing an experiment to help me understand this reading better. So the reading I'm trying to understand is this. And then I'm going to say, here is my experiment. Does my experiment make sense? Is my experiment working or not? Is my experiment working or not? How can I improve upon my experiment so that I understand the reading intuitively?
Your experiment appears to be focused on understanding the nice command and how it affects process priority in Linux. Let's break down your experiment step by step and analyze it. You started a process with the highest priority, -20, that sleeps for 5 seconds and then prints first. You started a second process with the lowest priority, 19, that sleeps for 15 seconds and then prints second.
Yes.
You checked the background processes with the jobs command and found both processes to be stopped. You attempted to run similar commands but without the sleep, and both processes were stopped again. Observations. All your processes are in the stop state.
Oh,
This is because you're using sudo with a background command, and in many Linux systems, when you run a background command with sudo, the system is waiting for the password, if not cached, to authorize the action, which effectively puts the command in a stop state.
That's why. Okay, got
This is
it.
the core issue with your experiment. Improvements.
That
Avoid
makes
sudo
sense.
for experiments. You can create processes that don't require root permissions to see the effects of nice. If you must use sudo, enter your password first to ensure it's cached.
Yeah. I'll do
Extend
that.
iteration. Processes such as echo finish almost instantly. They don't allow you to observe the behavior over time. The sleep command you initially used is more appropriate, but you might want even longer durations for clear observation. Monitor in real time. Use tools like Top or HTOP and Nether Terminal to see how processes are prioritized in real time. Introduce CPU-bound processes. Instead of sleep,
Oh,
which is
that makes
IO-bound,
sense.
use a CPU-bound command that will genuinely compete for CPU time.
Oh, it's IO bound.
For example, the following
Okay.
command simulates CPU work. JavaScript copy code is greater than dev null, and a revised experiment might look like this. Open 2 terminal windows.
Oh, that's
In the
good.
first, launch HTOP or top to monitor processes.
Ooh, beautiful.
In the second terminal, run. Without filling the first process, run. Observe in HTOP or top how the CPU utilization differs between the two processes.
Beautiful.
The high priority process should consume more CPU than the low priority one. Kill both processes when you've made your observations. This should provide a more tangible experience of how nice values affect process priorities.
Ooh, let's do it. Let's do it. What a world we live in. I'm like, everything is different. If you're not using it's $20 a month. Like, and it doesn't even, I'm a salesman now, I guess, but it doesn't even cost that much. I mean, there's free functionality. It's like, what a world. I never, this is what I needed my whole life, because I've always had these questions I'm asking it right now. I've always had questions like this. And like, when I ask these questions, here's the answer I get. Duh. So it's like, you know, this is changing my life. Okay, so let's see here. So let me try the okay, so we're gonna try the experiment as I came up with it, which is not as good. Yep. So there we go. Okay, well, you know what? It worked because we got second printing out there. And let's see what happens next. Oh, you know what? It didn't work because let's see here. I don't know if it worked or not. Oh, it's my terminal. God damn it. What the hell? Okay, yeah, it printed out the first here and the second there, so really just not my experiment is, of course, you know, just poorly designed. So let's use the experiment from the AI. What? Uh, why can't I kill these two jobs?
When the job is stopped, it means it's not actively running. It's suspended and not executing.
Oh.
The jobs in your list are in the stop state likely because they're waiting for some input, as is typical with sudo in the background. To kill the jobs, you have a few approaches. Using the FG command. This brings the job to the foreground. Once in the foreground, if it's waiting for sudo password input, you can provide the password or just press Ctrl+C to cancel the job.
Oh,
Bash
okay.
copy code FG%3 then. Bash copy code FG%4 killing by job ID. Use the kill command with the job specifier. Bash copy code kill%3 kill%4 killing by process ID.
It's because I saw something like really weird. Like, you know, it's prompting me for a password. So it's like, you know, I'm not only running sleep and echo. Like, I'm running whatever process prompted me for that. You know, I'm running sudo. So it's like sudo doesn't work the same. So it's like, I mean, now that I have sudo in there, maybe it works. Let's try it one more time. Nope, still first, still second, and then probably still hung as well. Oh, not hung now that I have CPU and the sudo password in there, but not a good experiment at all. Let's do the experiment that the AI gave. So we're gonna have two windows. Let's make one like that, and then one like this, and then we're gonna have the first one run I kind of want to run htop, but let's just do top because that's, you know, on the LPIC maybe I won't be able to use htop, so we're just gonna have top, and let's sort top by well, you know what, let's just leave top as it is, and then we're not going to use this IO bound process sleep. Instead we're going to use a CPU bound process, and the process is yes. And then we're gonna do we're gonna redirect the input to dev null, which means the standard output of this is just gonna go nowhere. It's gonna go in the trash bin, and then we'll use the ampersand to make it run in the background. All right, and now we should hopefully see a yes process form in top. We might need to organize top by CPU percentage. So let's ask the AI. How do I rearrange the output of top to show CPU utilization first?
B. Top command provides a dynamic, real-time view of system performance. The display order of columns in top can be changed interactively while the top command is running.
Yeah.
Here's how you can rearrange the output of top to show CPU utilization first. Start top. Bash copy code top enter field select mode. While top is running, press F or F to enter the field select mode. You will see a list of available fields that can be displayed, each with a letter associated with it. Each field will also have either a next to it, indicating it's currently displayed, or a space, indicating it's not displayed. Locate the CPU utilization field. Look for the %CPU field, or a similar name depending on the top version and platform. Take note of the letter associated with it. Change the order. In field select mode, you can use the arrow keys, or J and K in some versions, to navigate up and down the list. Move to the %CPU field. Once highlighted, you can use the right arrow key, or D in some versions, to move it to the top of the display order. Exit field select mode. Press Q or enter to exit the field select mode and return to the main top display. Save the configuration. If you want top to remember this configuration for future sessions, press W, capital letter W, while in the main top display. This will save your top configuration to a personal configuration file, usually located until...
No, that's not what I want. What I meant is I want the process IDs to be displayed under the columns so that the rows of the process IDs are organized by the percentage of memory that the process is consuming.
Got it. You'd like to sort the list of processes by their memory utilization.
Right.
Here's how to do it. Start top. Bash copy code top while top is running. You can change to sorting column. For most versions of top, press M, capital M, to sort by memory usage. The processes that use the most memory will be shown at the top. If the above doesn't work or if you want to use an alternative method, you can also change to sorting column interactively. Press the less than and greater than keys to navigate left and right through the column headers. Navigate until the %mem column is highlighted. Once %mem is highlighted, the list of processes will be sorted by memory utilization. After following these steps, the processes in top will be listed in ascending order based on their memory utilization.
Okay, I think this is it. So basically you scroll through. Yeah, so we can now see we've got this process ID 5116. taxing 100% of the CPU. So it's taking out an entire CPU just for this process. And there we go. This is 116. So we've got it sorted correctly. So let's continue doing the experiment. All right. So here we go. So we got two terminals. The first one is top, sorted by the CPU. And then the next one, we're going to run these two here. Okay, and this is just an example of a CPU bound versus IO bound command. So this is not part of the experiment. I'll just stop this right now. So we're going to do kill %1, and then we'll see that go away up there. Now these are the commands we actually need to run. The first one, we're going to set it to be the least nice. Okay, so we got sorry. Permission denied. So, but the thing is, it's running. Do we have a job for it? We do. Let's kill the job. And then let's just do the sudo echo. There you go. Give it the password. All right, and then we'll do a jobs, nothing. Okay, and now we'll put in this first one. There we go. And now we'll put in the permission denied again. Well, let's put in the second one anyway. Okay, so now we've got process ID 5124 taxing out the CPU. And then we've got 5125 is listed second here. 5124 is using more. 5125 is using less. Looks like a lot of the times they're using the same amount, but I have yet to see 5125 use more than 5124. All right, so now we observe how the CPU utilization differs between the two processes. The high priority process should consume more CPU than the low priority one, and we have been seeing that for the most part. It is the same, but we have not seen the. Oh wait, we just saw the lower one take precedence. Yeah, we see that again. So okay, so I ran the experiment and I see that the nicer one actually does sometimes use more CPU percentage than the one with the least nice value, but for the most part they use the same CPU percentage.
Your observation is an interesting aspect of how the Linux scheduler works. The nice value is a hint to the scheduler about the priority of the process, with negative values being higher priority and positive values being lower priority. However, the scheduler uses the nice value in conjunction with other factors to determine how to allocate CPU time.
Okay.
A few key points to consider. Other processes. If no other processes are competing for CPU time, then even a process with a high nice value, lower priority, will get CPU time.
Yeah.
In such scenarios, you might observe that both your high priority and low priority processes are getting about the same CPU percentage. Dynamic prioritization. The Linux scheduler also dynamically adjusts the priority of processes based on their behavior and their recent CPU usage. This ensures that both CPU-bound and IO-bound processes get fair access to the CPU. So, even if a process has lower static priority, due to its nice value, the dynamic priority adjustments can still allocate its significant CPU time. Experiment duration. It's also essential to consider the timescale of your observations. If you're only observing over a short time frame, transient factors can affect your results. Running the test for longer durations or multiple times can give you a more consistent view. System load. The effects of process priority become much more evident under high system load. If your system is mostly idle, then even the low priority processes will get a lot of CPU time. But if the system is heavily loaded with many processes competing for CPU, then the difference in CPU allocation based on nice values will be more pronounced. To make your experiment more pronounced and see more significant effects, introduce a competing CPU-intensive task without a modified nice value. Use longer running tasks rather than short-lived ones. Run multiple instances of both high and low priority tasks. Monitor over longer periods to see the cumulative effects. Remember, the nice value is just one factor in a complex algorithm the scheduler uses. It's not a guarantee of CPU time, but rather a hint to the scheduler about the desired priority of a process.
Okay, so now we can see the one that is least nice is jumping to the, well, they're all kind of the same. That's interesting. I mean, they're all like the same kind of intensity. So like, yeah, they all use the same. We do see, yeah. So I don't know. It's probably not that great of an experiment. I think I'm gonna end the video here. It's just going on too long. We still got the exercises to get through, which we'll probably go through this, and you know, it's better than I can come up with on my own or even with the AI. So let's end the video here, and then when we come back, we'll go through the actual exercises. So first thing I'm going to do is pkill. Well, first thing I'll do is jobs. See, we got these jobs, so I'm going to do pkill on yes, and then jobs again. There we go. Now we got those done. So yeah, that's it for this video. Stay tuned for the real exercises, which are hopefully better than these. Thanks for watching.